Hello everyone, and welcome to today's webinar titled Modeling Florida Lakes with Bathtub. This webinar is sponsored by EPA's Water Quality Modeling Workgroup. My name is Jason Gilday with US EPA, and I will be moderating today's webinar. Thank you all for joining us today. So first, I'm going to briefly summarize some of the features of today's webinar. We hope you will have a lot of questions, and please submit your questions in the presenter questions box on your control panel. If you have problems viewing the broadcast, just let us know in the Adobe Connect help box, and we will post an answer in that same box. This webinar will be archived for later viewing on EPA's Water Quality Modeling training page, and we provide that archive link for you at the bottom right of your screen. Also, at the end of today's webinar, you will be able to obtain a certificate of attendance for participating, and we'll provide directions for downloading it at that time. The materials in this webinar have been reviewed by US EPA staff for technical accuracy. However, the views of the speakers are their own and do not necessarily reflect those of US EPA. Mention of commercial enterprises, products, or publications does not mean that US EPA endorses them. So to quickly cover some more logistics, the purpose of today's webinar is to help water quality professionals better understand water quality modeling and how models can be used to solve problems facing water quality regulators. The target audience for the webinar series is a water quality professional who may use, want to use, or review models as part of their job, but who do not necessarily have a modeling background. As such, we are assuming that the audience has a basic understanding of water quality science and concepts, but has limited direct modeling experience. Today's webinar is the 22nd in our water quality webinar series. All of the past webinars have been recorded, archived, and posted to EPA's YouTube channel, and links to the archived files are available on our Modeling Workgroup website. Again, the URL is shown at the bottom right of your screen, and further in a few weeks, a copy of today's webinar archive will be posted on the same website. We encourage you to listen on any of the previous webinars or share access to these broadly. The webinar series do sort of build off one another and start with modeling basics and expand into specific models and different topics as being shared today. So with that, I'm pleased to introduce our speakers for today, who are Erin Rasnake and Ansel Bubel with Florida DEP. And Erin is the program administrator for the Water Quality Evaluation and TMDL program with the Florida Department of Environmental Protection's Division of Environmental Assessment and Restoration. She has spent 15+ years coordinating and working with state and federal agencies on water quality issues and restoration. Erin earned her MS in Environmental Science and BS in Environmental Studies degrees from Florida Gulf Coast University, and her MS work focused on relationships between seasonal and spatial variation of contaminants on the health and physiology of oysters. She's a native to Florida who enjoys outdoor activities, including fishing and Tampa Bay sports. Our next speaker, Ansel, is the Environmental Administrator of the TMDL section at the Florida Department of Environmental Protection. He has worked on solving water-related issues for 7 years, with 5 years of experience specifically focused on TMDL modeling. Ansel holds 2 master's degrees from Duke University, including a Master of Environmental Management and Water Resource Management, and a Master of Forestry and Forest Restoration. Additionally, he holds a bachelor's degree in geology from Williams College. And with that, I'm done, and I'm going to hand the floor over to Ansel to kick off today's webinar.
All right, welcome everybody. We're here to talk about Bathtub. But before we dig into the specifics of the model, of the Bathtub model, I want to talk about models in general to help situate Bathtub in the kind of suite of models that are commonly used for water quality analysis. And I guess a primary thing we have to talk about is why do we model in the first place? Because models take time to set up, but they're very useful in a number of scenarios. So the first thing is we might not, in most aquatic systems, we don't have perfect knowledge about the system. We don't have a sonde out there in every single part of the water body, collecting water quality information 24/7. So there's some need to project information for where we may lack it. Additionally, we may want to deal with management questions in which we may need to ask questions about if we change something about the system, how the system would respond. And so models in both of these two cases can give us answers and are very useful tools. To simplify models down to two polar examples that obviously the real world is a little more complex, the simplest kind of models are empirical models that would use observed relationships between water quality parameters, usually a nutrient concentration and a response variable like chlorophyll, to derive a simple regression type line and predict water quality based on that. On the other hand, we have process-based models. Up here you see the WASP, advanced eutrophication process diagram, and this very complicated model like this is keeping track of the fate of multiple species of nutrients, of carbon, chlorophyll, dissolved oxygen, and it's predicting the actual processes underlying the behavior of the system. And so these form sort of two polar ends of the water quality modeling world. But the fundamental differences are you predicting the world based on things you see in your system in an empirical relationship, or process-based, which is based on literature relationships that then you kind of tune for the system you're working in. And one thing we have to consider when we're choosing models is the kind of water body we're working on, because the configuration and the flow type drive behavior of the system, and that behavior, which we're going to try to match with the model, we have to make sure our model choice can predict the dynamics in question of our system. And when we look at the kinds of systems we see in Florida, we've got springs, streams, lakes, estuaries, and these systems can behave very differently, have very different residence times. They can have different kinds of flow, and we'll get into that, but just you have to think carefully about your system before choosing a model. So the first thing to talk about is the flow regime. And we have, if we can break our world up into three main water body types. So streams, our classic understanding of stream hydrology would come from somewhere like Coweta in North Carolina, where our flow is all gravity-driven based on bed slope. And some Florida streams are like that. Other streams are tidal creeks or areas where there may be bidirectional flow. But in that case, it's still like a one-dimensional or one-dimensional reversing flow. For lakes, we have maybe two different configurations. We might have some small sinkhole lakes that are generally well mixed, and because Florida lakes tend to be warm and shallow, we don't tend to have stratification. Our larger lakes, on the other hand, may actually have three-dimensional water movement. So we have to make a choice based on what we see in terms of water movement about the model we use to represent it. Finally, estuaries are always had three-dimensional water movement because you have fresh and salt water meeting, you have tides driving reversing flows, and then you have different densities when you have fresh and salt water. So you pretty much have to deal with a three-dimensional hydrodynamic modeling when you're talking about estuaries. So in terms of model dimensionality, as I mentioned with the flow regime, you want to choose a model that can represent the real dimensionality of the system in the sense that it affects behavior. So for a small stream, some of these tributaries we see on the upper side of the Colusa-Atchute watershed, a one-dimensional model, stream model like HSPF would be an appropriate choice. On the other hand, if we're looking at an estuary on the left side of the diagram or the lake on the right, which is Lake George, those are systems where we have three-dimensional water movement, when we'll need to choose a model that represents that accurately. When we look at water quality models, there are a number of things to consider. So as we sort of alluded to before, there's a range of complexity from our regression models on one end to a complex process-based model like WASP or C-Qual ICM on the other hand. But another aspect of this is what time step the model is actually using to predict the behavior of the system. So our simple models tend to be run on an annual time step, bathtub and regression, whereas HSPF and WASP and C-qual are all run at a daily or an hourly time step, which is required to run those more complex process-based equations. Now, if you're dealing with a phenomenon like dissolved oxygen, where you need to predict daily behavior, you pretty much need to use one of the models on the right. But if you're dealing with a well-mixed system that reacts at a slower time scale with a longer residence time, the regression or bathtub approaches will give you good answers for those systems as well. An additional question here is what data you have. Do you have enough data to parameterize one of the models on the right? If you're talking about a small lake, you often do not have sufficient data to parameterize one of those models. So you have to deal with your input data and make an appropriate model choice based on the data you have available. And sort of as I've been sort of describing, there's this range of complexity. And we generally have 3 different steps of models that we use in Florida. So our simplest would be a multiple regression on annual mean values. Our moderate complexity would be a watershed model feeding to a bathtub model. And our most complex model option would be an HSPF watershed model going to an EFTC hydrodynamic model feeding a WASP water quality model. So now we come to Bathtub. Bathtub was developed by the Army Corps of Engineers specifically for reservoirs in the southeast of the U.S. It was originally developed in 1981 in Fortran and then updated in 1999, and somewhere along the way they converted it to Visual Basic in a graphical user interface format, which we use today. So Bathtub is a model that is a hybrid of a mass balance calculation type model with empirical driving functions. And so I'll describe that in a little bit more detail, but in terms of estimating concentration, we need to know the flow and nutrient loading of nutrients from the watershed, the dimensionality of the water body in question, and then information about precipitation and evaporation, and that will predict inlet concentrations. From those concentrations, Bathtub uses observed relationships to real-world water quality data to predict chlorophyll. So Bathtub natively deals with conservation of mass from a number of fluxes, and these deal with both movement of water and of nutrients that goes along with it. So the primary driver is watershed input. Then we also have direct rainfall that usually carries nutrients with atmospheric deposition. We may have evaporation off the surface, which will remove water. And in the lake, we have both sedimentation, which removes nutrients, and internal loading through either end fixation or from sediment nutrient flux that could return it to the lake. Once Bathtub has predicted the in-lake concentrations, it uses observed stressor-response relationships, essentially an empirical regression, to derive the resulting chlorophyll concentration as a function of input nutrients and residence time. One question about Bathtub, or one aspect that we may want to consider, is how we split up our water body. So Bathtub is capable of representing a water body with more than one cell. And so the canonical case for Bathtub is a reservoir where you have different behavior as you move downstream in the reservoir and the dimensionality changes. For Florida lakes, we may find some lakes that are long and linear and for which nutrient concentrations and chlorophyll dynamics are different at one end or the other. And the ability to break those lakes up is very important, and Bathtub allows us to do that. So you want to think about the dimensionality of your system before you're setting up your Bathtub model, so you can set it up in a way that's most accurate and capture, and in a way that captures the real-world dynamics of the water body that you actually observe in your data. Okay, so we've talked about this a little bit before, but what do you actually need to set up Bathtub? So the fundamental pieces of information you need to understand the dimensionality of the water body, including its length, width, and average depth. Now, obviously, when you have a shapefile of a water body, that water body is going to be kind of blobby, for lack of a better term, and you basically need to come up with the closest rectangle that approximates it in order to get an average length and an average width, because all that combines to get a volume. So you basically want to get the correct volume in there. Additionally, the main driver of water quality will be your watershed loading. And you can use any watershed loading model to get that loading. We commonly use PLASM or curve number model when we're using Bathtub, but models have been run in places where we have other models set up. So we have driven it with WAM or LSPC or HSPF, where those models were already set up. And Bathtub works just fine no matter which other model is providing that input. Additionally, atmospheric deposition can be important, and Bathtub natively considers that. So if you have local data, I recommend using the locally measured data if you could find it. Otherwise, you can use a national rate or an average rate. Finally, additionally, rainfall on the water body is important in the sense of dilution, potentially, of your nutrient concentrations. And finally, if you know and have a measured nutrient flux, whether that's end fixation or sediment nutrient flux, you can put that in as a steady flux in Bathtub. Now you want to make sure that those numbers are based on some sort of measured data, whether regionally or in lake. But Bathtub makes it easy to enter those fluxes if you know what they are. And finally, observed water quality data is important so we can check our model to make sure that we're actually reproducing the real-world conditions that we're hoping to model. Bathtub can take other kinds of inputs to the water body, or to your water body, if you know what they are. Now, the most common thing we consider in Florida are sometimes groundwater inputs if we have either a superficial aquifer that may be contributing water, and or if we have septic tanks that contribute load to that superficial aquifer that makes it to your water body. This is not, some models find that this is important, others don't, but it's something that you can add in. Now you have to, in Bathtub, kind of trick the model to do this because there's no place for it to take a groundwater input. You have to just treat it as another tributary. So the use of extra tributaries to add additional load is a way that you can add other sources of nutrient loads if you happen to have data or valid predictions of what they might be. So within Bathtub, in fact, there's not just one set of driving functions. And just like something like the WASP model, you can use different formulations to figure out your nutrient concentrations and then your resultant chlorophyll expression. Now, one could delve into these equations and spend an entire hour talk just on these equations, but I will point out that different equations consider different constituents. So, for example, model option 1 considers phosphorus, nitrogen, light, and flushing or residence time, whereas model 2 considers phosphorus, light, or flushing. And so that model choice should be matched, if possible, to what you understand about how your water body is responding. In other words, if it's co-limited, you would want to use one of the models that considers phosphorus and nitrogen. Similarly, nutrients, both nitrogen and phosphorus, have their own predictive equations. And in general, what we're sort of trying to get at is what is the role of sedimentation here in removing nutrients. Again, we could spend a while going through these constituent equations, but it's all laid out fairly well in the help manuals. So So I'm going to just keep on moving here to keep it lively. Phosphorus has pretty much the same model options as nitrogen. Okay, so in terms of actually using Bathtub, there are some considerations. One consideration is you're probably simulating multiple years worth of time, or at least I hope you are, because you want to have multiple years to actually capture real-world environmental dynamics. And so when you're simulating that in Bathtub, one question is how you deal with multiple years, because Bathtub natively doesn't have a way to have a multi-year simulation. So one way to do it is to add an additional segment for every year, and I'll talk about what that is in a minute, and have one input file that contains all the years of segments, and there'd be a different watershed loading to every segment for every year. The benefit of that is if you add observed water quality, you can create calibration graphs in the Bathtub model itself. You may run into a limitation, however, because Bathtub can only take, I believe, 64 total tributaries. So if your system is very complex, or you're simulating a very long amount of time, you could run into limitations with that approach. So you can additionally have one model input file for every year. Just a choice that the modeler has to make, but one to be cognizant of before you jump into setting up the model. Okay, so calibration. Like other models, you want to consider calibration in the order of getting your flow right, then your nutrient concentrations right, and then your chlorophyll. Now, for flow, hopefully you have calibration on your watershed model if you have a station. And flow calibration is possible if you have observed flow data, but there are many cases in which one has to model a water body and there are no flow stations. So that is recommended if you have the data to do it. For nutrient concentrations, you obviously want to match the observed water quality data, and then you can move on to the chlorophyll to make sure that the correct response variable is being predicted. One thing to note, in Bathtub there's a feature called auto-calibration. My personal opinion, don't use it, because it calibrates by using a multiplier, and I have observed a case where if you put in data, it will calibrate it almost whatever you put in. So I've seen a case where there was just a trial run and there was a units error, and the inputs were off by a factor of 1,000, and Bathtub stuck a 1,000 times multiplier in there. So I never use auto-calibration, and I would recommend you be very careful before using it, or if you do use it, check the results very carefully. Let's talk about the interface itself. So there's obviously a prominent run button, but most of the actions you will take involving Bathtub involve the first four menu options. So case allows you to read an input file, it's a pull-down menu. The edit menu contains all of the screens for editing segments, tributaries, global variables, basically the stuff that makes Bathtub run. The run button obviously makes it run. And then for outputs, you can either use the list function, which will send outputs to Excel, or you can use the plot function, which will create calibration plots. And so in particular, the screens that you'll use most, so global variables is one of the first ones you want to set, and in that screen you're setting your meteorological variables like precipitation, evaporation, and your atmospheric loads. And these are applied to all segments within your water body. Next, you want to set up your segments themselves, which are the average blocks where you're building your water body, whether that's one or several. And you can control, in that outflow segment in the middle of the screen, you can control where they flow to. So you can rapidly set up a system where you have 3 segments all on a line flowing to each other. And Bathtub makes that connectivity very, very easy. And again, the key things you want to add in here are your morphometry down at the bottom. The next step will be adding your tributaries, and again, these are your nutrient loads primarily this will be from your watershed model. And one thing to note, so you can give it a name, you can mention which segment it's flowing into in the middle of the screen. But one thing to note are the units. They're a little bit funny. So the flow rate is in hectometers per year, cubic hectometers per year. I honestly have not come across that unit anywhere else. Just be aware of that because you have to do that unit conversion before putting your flow in. Additionally, concentration is in parts per billion. An easy units conversion if you're dealing in milligrams per liter, but just be aware of that because it's kind of peculiar. But just to note, if you were if you had groundwater input, you would put this in as a tributary, just like you would with your input stream. So this is the sort of catch-all where you can add additional nutrient categories, loading categories, if you have the data to support them. And finally, as I mentioned, when you're using Bathtub, you have to choose the driving functions that you're using to calculate nutrient and chlorophyll concentrations. And there's this model selection screen where you make those choices. And those models are applied to all segments that you are simulating in a given Bathtub model run. And finally, when you're calibrating, there's a calibration screen where you're adjusting the calibration parameters. And there's pretty much only one knob for phosphorus and nitrogen, and there are recommended ranges for these. So phosphorus, I believe, is from 0.5 to 2, and nitrogen is from 0.3 to 3. I checked the manual on that. I'm about 70% sure that's correct, but pay attention because the manual lays out the acceptable ranges for these parameters. And finally, once you have a simulation, the Bathtub will allow you to create quick plots to allow you to evaluate your calibration and then to go in and make adjustments as needed. And because all of this is contained within the model, you can move quite rapidly from setting up your model to calibrating because of the limited number of calibration parameters and the ability to compare results in the model itself. And finally, if you want to output the model predictions and create a publication-worthy graph, the list menu allows you to output data to a spreadsheet, and you can output information on hydrology, on loads, on concentrations, on residence time. You can output almost anything you would want from the model. So exploring that menu is useful in case you want to evaluate your data with something other than the native graphing capabilities. And at that point, we'd be happy to take any questions that you might have on the function and setup of the Bathtub model.
So hi everyone, this is Jason again. I'm going to moderate a quick question and answer session here. Just to remind folks that you can type questions in for Ansel in the presenter questions box. I see we have a few, and I'll get to those in a minute. There'll also be another question and answer session at the end of the webinar and after Erin is done presenting. And we'll use whatever time we have to get through the main questions. Just a reminder, I like to remind folks on these webinars that we'll be taking questions on the technical matters today surrounding Bathtub and the different examples that Erin and Ansel are going to present. But if you have more policy-related questions regarding what was done in a specific watershed, I would encourage you to reach out to Ansel and Erin directly. And with that, I'm going to just start at the beginning of the questions. Ansel, the first question says, what about seepage in the model? I'm assuming that means does the model account for seepage, and can you explain how that might work?
So the model assumes there's no input or output from the lake, but as I mentioned, you can, if you assume this, so seepage could be in or out of the lake, right? So if it's coming into the lake, as I mentioned, using that tributary screen, you can put a diffuse seepage in as assuming it's from a superficial aquifer. Now, if it's seepage out, as in like seepage either groundwater flow out or groundwater flow down to a deeper aquifer, I think there might be a way to add an additional segment and put a monitored outflow to basically pull water from the model. I haven't done that before, but you would want to understand the directionality, and you would want to, Bathtub won't natively do it. So you as a modeler would have to have a good, well-bounded estimate of what that seepage would be. But if you know what that seepage is, I believe there's a way you can input it in, whether it's a flow in or out.
Thank you. Next question is, if there were real-time TP data, would that enable more complex HABs predictive modeling compared to Bathtub? And maybe just in general, Ansel, to maybe comment on your experience or what you would think about using Bathtub to look at HABs. I know that it's a really important topic that a lot of people are interested in these days.
So Bathtub considers a yearly average condition of the lake, and so if your HABs are a chronic condition and show up as an elevated annual concentration in certain conditions, like one of the examples that will follow, the lake was very sensitive to drought years and would have elevated chlorophyll in drought years, and the model is able to predict that behavior of higher average chlorophyll under certain conditions. Now Bathtub, like many other models, is not considering individual species, so it's considering phytoplankton as an aggregate. And because it's on an annual time step, it's completely out of scope of the model to predict a short-term acute event that might last a week or two. So if your HABs match the timescale of the model and it results in an average condition, it can match it. But otherwise, many algal blooms may be at a different timescale than this model is working at.
Thank you. I'm reading through a few of the questions, and some of these are pretty specific to individual slides you had. The next question is your use of Bathtub incorporated phosphorus monthly, quarterly, or semi-annually?
Well, so Bathtub is run at an annual timescale, so you could average those phosphorus results and compare your annual phosphorus to your model predicted annual phosphorus. But the model runs at an annual time step.
Okay. I think that also answers the next question in the chat box, so I'll move on to the one after that. Have you ever used Bathtub to answer the hypothesis that internal cycling of nutrients is more dominant than the lake's nutrient input flux? So I think the question is getting at internal cycling versus inputs and how that may be accounted for.
So Bathtub deals with internal flux in the sense where you can add a rate and it will add it as a fixed rate. It can't predict the processes of internal loading based on, let's say, sediment conditions. So it's not really the best tool to make a decision about whether internal flux is going on or not. There is a whole body of literature about measuring either end fixation or sediment nutrient flux, and the short answer is there's three commonly used methods for estimating sediment nutrient flux. One would be chambers, and the other two involve cores. One is a core excavation, and the other is core pore water extraction. So those are the scientific, the approaches you see most common in the scientific literature. A model could suggest that you were missing nutrient loads, but it won't answer the question of where it's coming from.
Okay, thanks, Ansel. And I'll remind folks, because we are doing only a very few number of question and answer sessions, as you type in your questions, if you could be as specific as possible to what you're asking. I realize some people are typing in questions as they see an individual slide and maybe have a couple word question typed in, and it's a little out of context at this point. So I'll do the best I can, Ansel, to interpret what people are asking. But if you have a clarification on a question you've typed in, please feel free to add that in, and I'll try and get to it. So we'll take I think we have time for a few more. How exactly is evaporation included in the model? Is there a specific formula or is it rate-based?
So it's based, I believe it's just an annual height of water evaporated in terms of inches. I'd want to check the bathtub model before, don't quote me on that, but I think, as I recall, that's the way it works.
And maybe, Ansel, real quick, this is for me. Is there a website with a manual? Maybe you guys are going to cover that later, that people could look into more, under the hood and get more specifics on those type of questions?
When you download the model, it comes in this directory called Simple Tools that comes with these other models called Flux and other things like that. But included in the Bathtub files, there is a compiled HTML help manual that's actually very good. And so if you download it, you find that help manual and go through it, because pretty much everything I learned about Bathtub was from basically poring over that help manual. And additionally, the authors, Dr. Walker and the current maintainer, Dr. Sobal, have produced some PDFs that document the way the model works as well, so that there is good documentation on the model.
Great, thanks. And Ansel, where do you download it from? Can you just Google it and it would pop up, or is there a specific agency that maintains it now?
The Army Corps produced it originally, and the Army Corps still posts it.
Great.
And the contact is David Sobal, who's a former Army Corps employee.
Maybe a few more back to the technical questions. Do the equations you use for phosphorus already have internal loading incorporated into them?
No, because the equations are just considering how do you come to the concentration of phosphorus.
Okay.
I mean,
and
there's both sedimentation and nutrient flux, and there's some balance between the two, right? And there's some lakes where they're abjectly losing nutrients to the sediment, and there's some lakes where they're in net gaining massive amounts of nutrients from the sediment. But most lakes, those two are kind of going against each other, and you could set a rate that would kind of net the sum of those two things, right? But so it's possible to calibrate it to kind of incorporate both of them if you have a middling rate of sedimentation and flux, but if you have high rates of flux or sedimentation, you need to deal with that separately.
Okay, and the next question is, could you just, I think there was maybe some confusion on the flow units that you presented earlier. The question was just, could you go over those again, and what kind of conversion factor, do you have conversion factors for million gallons per day or CFS?
It's hectometers per year, and you just, honestly, whenever I go in there, I kind of just look it up again. I don't have like a standard formula, but again, you can look it up. You can figure out what that is based on your units, because some models are acre-feet per year, others are CFS, others are MGD. So just kind of look it up based on your flow units.
Next question. Could you comment on how the error compares when using Bathtub versus the WASP HSPF models? And I'm thinking maybe the more generalized question would be, could you compare maybe a quick overview of the difference between WASP and Bathtub? So that would probably take a while, but
Erin also has an example that she'll get into that deals with an actual comparison we made. But the main difference is that WASP can resolve like fine temporal scale dynamics in the water body. But if you think about a water body, the main drivers of what happens in a water body are generally really how much rains on the watershed is the main driver of interannual variation. And then that rainfall is driving nutrient loading. And generally the question of, I don't know, how eutrophic a water body is usually a ratio of how much, how enriched the landscape is with nutrients compared to kind of how much the water body can take versus how much its criteria is. So the short answer is that when we've compared them, if you were asking, you know, what kind of a management scenario you would need, we tend to get surprisingly similar results in terms of what kind of nutrient reductions you might need from Bathtub versus a more complicated model. Because fundamentally they're all making the similar assumptions and they're working with the same system. So there should be a common answer that they arrive to if you've represented your system correctly.
So maybe some questions along those lines then. For Bathtub, is there like a depth cutoff or a size cutoff or a variability cutoff where you just wouldn't use it anymore? I'm lumping several questions from the chat into one.
Good question. I don't know if there's a depth cutoff. I know it was created for reservoirs in the southeast that probably aren't deeper than 50 feet. I know in Florida we've applied it to lakes that are about 20, 25 feet deep. So I guess what my point is, if you were talking about like a large northern lake that was 200 feet deep, like a Great Lake, I don't know the answer whether it applies to those lakes, but yeah, I'm going to say that's one I don't know the answer to.
Okay. Well, maybe following up on that answer, in your, would you recommend using Bathtub in some of these more northern lakes or even western lakes, or because of the way it was developed, is it really only applicable to southeast lakes and reservoirs?
I've only ever used it in Florida, so that is an excellent question, and I'm going to say I don't know the answer to that.
Okay. I think we have a minute, maybe a couple more minutes for questions, and then we'll move on, because there are quite a few more on here. It's great. Do you have a specific internal loading calculation method that corresponds? Sorry, the question got cut off a little bit. I guess, do you have a specific internal loading calculation method is the question.
It depends on whether you're talking about sediment nutrient flux or end fixation. For end fixation, we have some measured data in Central Florida that we use, and so we tend to use the nearest, we try to find measured data from a similar water body, and we use that measured end fixation. For sediment nutrient flux, you pretty much need a water body specific measurement of it. I mean, you could put a rate in there, but then it's sort of equivalent to putting in a black box flow into any other model. There's no way to check that result.
Got it.
You could do it, and you may need to, but just be aware that it's better to have some bounds on that. Okay, and maybe last question for now, because I realize we're running a little short on time, maybe. The question is, does the model take into account spring and fall turnover where the interactions with the bottom become less? So I think just in general, can the model do various turnover periods in any lake or reservoir? I don't think so. You can specify an epilimnion and hypolimnion depth if you know what the thickness of those layers are, but I don't think it allows those to turn over. But again, I've worked on lakes that don't really have a turnover, so. Right. Okay, with that, why don't we continue on with the presentation? Please keep typing in questions, and we'll have another question and answer session at the end. I also see there are a few questions about how to contact you and Erin, Ansel, and that information will be at the end of the presentation. We have email contacts for them both, in addition to how to get in contact with EPA and the EPA Water Modeling Work Group. So with that, we're passing it on to Erin, right?
Yes. So welcome, everybody. Thank you for all those great questions. What I'm going to do is kind of go over how Florida has developed TMDLs, with some of ours actually being adopted also as site-specific numeric nutrient criteria as new standards under some of our rulemaking. But I'm going to stay far away from all of that and really just focus on the bathtub modeling. Since 2001, we've adopted over 240 nutrient TMDLs with a combination of TSI, TNTP, chlorophyll, and DO. And of those, we've got over 30 lakes that we've used bathtub on. So for today's, I'm just going to kind of give 4 examples where we used a variety of approaches and inputs with bathtub to kind of show kind of more simple approach to the more complex. And then if you see in the slides where it's example applications Lake A, if you click on that letter A, it will link you to the final state adopted TMDL. And if you usually go to our chapter 5, that's all the modeling. And that way you can get a lot more detail, because as of right now, I put as many words as possible on a slide just because that's the way we've been trained to do. So you're welcome. Ansel did the simplest approach, and I'm going to give you guys more than you need to know. But with that, this Lake A is just a 50-acre lake, so kind of more on the smaller side scale. The watershed's only 720 acres, or the drainage basin, and this lake has an average depth of 63 feet. For this one, we actually didn't have any bathymetry data, so we had staff go out and collect that, and that's the map you can see. We also were able to estimate the runoff volume and coefficients using the curve number approach, and that was used in our pollutant load reduction goals, or PLRGs, which is part of our sister agency water management districts that create those models for us. We included rainfall, which we used, again, our local district's NEXRAD Doppler radar as an input. We also used our local land uses for maps, as well as some soil types. So again, a lot of GIS-based data going in. We also estimated the loading, and our time step for this one was 2000 to 2012. And again, we looked at rainfall volume for each land use type, as well as our EMCs, or event mean concentrations, for TN and TP. Again, the mean depth in lake surface area for this was based on the data we collected, as well as we had some annual groundwater seepage data that was provided by our county. So again, with any TMDL development and modeling, you want to make sure you have the most accurate and site-specific data. So Florida, we reach out early and often and work closely with our counterparts, because ultimately they're ones that are going to have to implement restoration. And then we also used what we call ARC inlet for our septic tank, or OSPDS loadings, and I'll talk about that in another example. Another lake that we just finished up is one of our larger lakes in Florida. It's actually a surface area of 850 acres, and the drainage is of 56 square miles. Again, the average depth is about 10 feet. This water body was designated as a surface water improvement and management priority water body in 1988. It was also, we worked with our local Southwest Florida Water Management District and local governments. They conducted extensive work within the lake and the watershed, where they collected paleolimnology studies, which we have a lot of that in Florida. So a handful of these lakes include that data as far as helping us with our TP target setting. Again, we used that PLRG I mentioned in the last example to get some of our pollutant loading reductions. Again, worked with them with water and nutrient budgets, as well as doing some source tracking. So this has all been going on over the last couple decades for this water body. Again, it's located in our west central region, where we have phosphorus-rich deposits, and there's some phosphate mining that still occurs today in this area. So again, it's slightly different than some of the other lakes throughout Florida. It's also hyper-eutrophic, and it's been impacted by point sources over the last 5 decades. But as of 1997, we finally got the rest of those out of there. So we're working on that Clean Water Act. As far as model configuration for this water body, we used the bathtub variable specific model, which we used TN Model 5, Model 6, and Chlorophyll A Model 3. We were able to calibrate by applying internal loading rate functions to approximate the measured in-lake mass. We were also able to calibrate using the bathtub calibration coefficient. And for this one, for the internal loading rates of for chlorophyll, we adjusted them each year. This lake is very unique in the fact that it has extremely high chlorophylls, and we had a lot of site-specific data that allowed us to do that year adjustment. Next slide. And then same, this is kind of showing some of the watershed in mapping. So what we did for this lake as well is we utilized the analysis of some sediment core results that we got from Dr. Whitmore, which again, that's kind of the paleo and chlorophyll targets. We also worked with our local soil and water engineering technology group, and they had created a WAM model, the watershed assessment model. So this was done previously as part of that SWIM, the surface water management thing I talked about 2 slides ago. And we had them update it with newer information, and we were able to apply those simulated observed lake conditions into the bathtub model. The third example is actually one that Ansel developed back in 2017 when it was adopted, but this is a larger lake. It's one of the larger lakes in Florida, which is 17,000 acres with a watershed of 367,000 acres. And again, the average depth is about 8 feet, but it does fluctuate. And I think there was a question earlier about that. So again, this lake kind of fluctuates, this one has a mean depth that's kind of a bathtub shape, so it's really deep in the middle and kind of shallow around the edges. The first example I mentioned had a lake stage of 55 feet to 66 feet, so we do have some variation, but a lot of our lakes don't fluctuate too much. But I think I saw a question there, so I meant to answer that. But back to this lake, it had 2 different longitudinal data sets that suggested that it's not well mixed and therefore should be represented by several segments in bathtubs. So Ansel had mentioned how you can do segmentation, and this is an example where we've done that. He drew 4 lake segments based on geological features that affect the mixing, and it was simulated which drain into each of the 4 lakes. I also want to mention, you can go ahead and click the next slide, that this lake itself is what we call the Cadillac of data sets. We had local data that collected weekly and monthly data for multiple years, and that for 10 years that we had nutrient data as well as speciation of all of that data. So again, this is kind of the diamond of our story where we don't always have all of this info. But for that, go back. That's okay. For the segmentation, it was basically it's that and the surrounding watershed. So the model input file is structured to reflect inputs calculated to each lake cell. And the model was run for each year from 2000 to 2014 with specific inputs for each of these contributing fluxes that are calculated. So again, here's kind of a diagram of how we entered all 4 and then ultimately out of the lake into the creek. And then as I mentioned earlier, there's this what we call ARC inlet, which is the nitrogen loading estimating tool for OSPDS and septic tanks. So it's a GIS-based model which was developed by Ming Yi at Florida State University. And he developed this model for DEP for us here in Florida. And it basically uses a cell-based Darcy flow to model the movement of nutrient plumes, which emanate what's coming from our septic tanks. And nearly all the phosphorus absorbs onto particles after moving through soil. So the ARC inlet really only calculates the nitrogen flux. And there's a link here as well in the header that goes to his website. And on there you can find his models are well documented. He's probably one of the best documented models we've seen to date. And he also just recently generated 7 hours of YouTube videos that goes through how to use the model as well as some local examples through Florida. Again, this is kind of Florida-specific modeling, where I know around the nation we have STUMOD and some other modelings to look at groundwater inputs. But again, this is a great resource if anyone's interested to go check out. And then as well for this Lake C, we included atmospheric deposition, and it was calculated as the sum of the dry and wet fluxes. The dry yearly flux was calculated using the per area rate from a local monitor, while the wet was calculated by weighting by the amount of precipitation that was in the lake. Nitrogen fixation was an assumed constant flux per year in both the current and background scenario runs. Light limitation was calculated using the derived formula you can see on your screen, which allowed the model to be calibrated using the color data transform to a non-algal turbidity, which would limit light in bathtub. Because 95% of the variation in chlorophyll is explained by color, calibrating using light was necessary to reproduce the observed chlorophyll A concentrations we had. And then the last example is kind of a special one. Again, Ansel stated that, the eutrophication response model of bathtub involves choosing one of several alternative models. And depending on whether algal communities are limited by phosphorus or nitrogen, or if they're co-limited, the suite of models also includes scenarios for algal communities limited by light intensity or controlled by lake flushing rate. The response of chlorophyll A concentration to the in-lake nutrient level is characterized by two different kinetic processes, whether it's linear or exponential. Loadings from other sources that we included in this lake was looking at the artesian input, base flow contributions, including our OSTDSs, atmosphere deposition directly onto the lake surface, and input from major rivers were considered in a loading estimation. Again, this lake's a 10,000 acre lake with surface area with an 87,000 acre watershed. Again, we used that curve number to look at some of our pollutant loadings. And again, looking at physical characteristics, meteorological data, and such that we've used in previous water bodies today. Within the model comparison, we looked at, so this one was originally developed in 2006. And like I said, we used that curve number and then lake model and simulated from 1995 to 2002. However, part of Florida's process is when we adopt TMDLs, we have implementation or a restoration program that we call our Basin Management Action Plans, or BMAP. And that was implemented in 2010. And part of that process, stakeholders brought up some issues with the original model in TMDL. They felt that the bathtub did not account for near-field and far-field effects of nutrient watershed loading, as well as nutrient contributions via in-lake processes, basically looking at that internal sediment loads and nitrogen fixation. So what we did is we put together a $600,000 contract to work with some of our counterparts, which is on the next slide. Go ahead. And we held 5 public workshops over the next 2 years. And so we worked with Tetra Tech as well as AMEC Foster Wheeler, and we took what we had existing models from our local St. Johns River Water Management District, where they had created an HSPF, EFDC, and WASP model as part of their PLRG. And the stakeholders had requested that we redelineate that HSPF watershed boundary with a finer resolution. They wanted us to update the BMPs within the model and extend the time period through 2013. Obviously, we had updated water quality data because a lot of the stakeholders went out to collect that missing information we didn't have originally, as well as adding some seepage flow data that Harvey Harper had collected as part of this contract, and obtained nitrogen fixation using WASP, as well as everything else on the screen that you guys can read. So with that, we did the exact same water body, HSPF, EFDC to WASP, and the results with the loading estimates between the bathtub in 2006 and then the latest and greatest 2017 model, we had a 1% difference in TN and 8% difference in TP, which we would expect the updated model to have marginally higher loads because it accounted for that sediment nutrient flux. And then we also went through and did some model scenario runs looking at the corresponding concentrations that matched those loads. And those came out and matched identical to what we had under the bathtub. So ultimately, the adopted TMDL that we adopted in 2006 was a simpler model that took, something we could do in-house. And it's still applicable and meets our water quality standards under our numeric nutrient criteria. We also did another scenario run looking at reductions for our BMAP. And again, those came out and met the TMDL, and we submitted this to EPA, and they approved that the existing TMDL is appropriate because part of, for folks that are involved in the 303D program, we had put this as a prioritization to revise, and ultimately we ended up not revising it because the modeling is correct. Yes, the complex models give you a lot more finer detail for allocations And some of those did shift in the watershed where we felt that certain areas needed to be prioritized higher. But overall, as far as meeting the lake concentrations and standards, Bathtub was appropriate. And with that, we're going to stop for some questions and leave our contact information if you guys have any questions. And I saw a lot of typing, so whew, let's hope I can answer all those questions.
Thanks, Erin. This is Jason again. I'll just pause and give people some time to type in questions. This is, I believe, the end of the presentation, right, Erin?
Yes, this is all we have as far as scripted slides.
Yeah, okay. So we should have plenty of time to get through some questions. Just a few things from me. As questions start to come in, please note that when the webinar is over, an evaluation survey will be brought up on your screen. And we really encourage you to answer the, take and answer the evaluation and give us feedback. We do read and listen to all the feedback and use that to improve our future webinars. So with that, I'm going to go back up here in the question box. I think there are a number of questions about, Lake A and Lake B and whatever are obviously some real lake in Florida, not something you've made up. And I think, Erin, if folks want to know more about those specific lakes and which ones they are, they can just contact you. Would that be a fair statement?
Sure. Yep. They can contact me, or when the slides come out, they can click on the hyperlinks, which is Lake A, Lake B, and it takes you to the final TMDL report that has all the details.
Great. Thanks. So next technical question. How was the in-lake mass measurement determined? By depth combined with linear sampling? Question mark.
Well, the model accounts for volume, and then you have measured water quality, which you assume, which the agencies that collect it try to collect samples in the center that are representative. So we assume that if we have representative sampling combined with the volume, that's giving us our in-lake observed mass.
Okay, thanks. Next question. Did the models for Lake A, B, and C include septic inputs as a, quote, extra tributary?
I did model C, so I'm going to speak to that one. That one included, or whichever one was yeah. So that one included septic loading as a separate tributary, exactly. That's the way that it typically gets added. I believe
A was done as well. I'd have to confirm on B, but yeah. I believe so.
And I will say, most lakes, in fact, do not have significant numbers of septic tanks, and for many lakes, we find we don't need a very detailed estimate of the septic tank loading. So if you only have 5 septic tanks, the precision offered by our inlet is not going to help you because it's only going to be a half to 1% of your overall watershed load.
Yeah, when we're developing models, we take a close look into the proximity of those septic tanks, because there may be some a lot up far in the watershed versus right next to a tributary. So we kind of look at buffer zones as well, right, which has been options we've looked at.
So like Lake C had 10,000 septic tanks all within a mile of the watershed, for example. So that was why our inlet was important for that one.
Okay, I'll just pause for a moment also to show folks that the certificate of attendance for today's webinar should have popped up in the bottom right-hand corner of your screen, and you can click on that and choose download files to download a PDF document, which you can then personalize with the names of everyone watching from your location. So it's bottom right-hand corner of your screen. Just click on certificate. So next question, when you talk about using the CN method, is that for continuous simulation model runs or annual average? And I'll let you answer that first. There's a follow-up question as well.
Yeah.
I think we're a little confused on the question.
Okay, that's fair.
What I guess the TN or CN? Well, I guess what?
Or CN curve number? I'm assuming that's what it was. Curve number. CN.
So the way that we use the curve number model is we use it to generate annual total volumes of surface runoff, like Horton overland flow basically, and then we apply an event mean concentration to that to get a load, and so we put that flow and load into Bathtub.
Got it. And then the follow-up question from the same person is, wouldn't the green amped be more appropriate for this type of analysis? I assume that is a similar type of analysis that you could do.
You can use that. Yeah,
okay.
you could use green amped. Sure. You can use you can use any watershed, any of the commonly used formulations for how you generate watershed runoff. As I mentioned, we've used when we've had like HSPF models set up. If we have one already set up, we've used that as an input. We've used, yeah, we haven't used green amped, but that's a viable approach.
Mm-hmm.
And then next question, I think is generally asking about dissolved phosphorus, total phosphorus, and what you need for Bathtub, and are there any correction factors in the model to account for the differences?
When you give your input data from your tributary loading, you give the concentration of total and of orthophosphorus. So the model is accounting for that inorganic to organic ratio.
Okay. When you're looking at chlorophyll A concentrations in any given lake, have you looked at the fraction of chlorophyll algae or chlorophyll A that is attributed to nitrogen-fixing algae? I guess maybe to more generalize the question, do you look at different algae species when you're modeling with Bathtub? And if so, do you look at the nitrogen-fixing algae?
So because Bathtub doesn't simulate different species, what you generally are looking at is just the total chlorophyll A concentration. But the only example I can think of is the example C. We actually had algal species data, and in that case, the high chlorophyll concentrations were associated with something like 95% cyanobacteria that could fix nitrogen. And so I was able to compare those population of nitrogen fixers with other proportional lakes, nearby lakes where they measured nitrogen fixation. So they would then measured it there, but they measured it on a lake that was 10 miles away. And I was able to compare the chlorophyll concentrations to assure myself that that rate was reasonable, and that kind of ground truth that nitrogen fixation rate that I used in there. So I guess the short answer is you don't use it directly in the model, but knowing if you have that information, it can help you be a little more precise about N fixation. But you can use most of the time, say somewhere between 90 and 99% of the time where we use the model, we don't have that data.
Okay, I'm going to lump a couple of questions. In terms of either septic systems or point sources when you're modeling, maybe septic systems first, is there a distance away from the water body or a distance proximity to the water body where you either include or don't include septic systems in your modeling in Florida?
We don't have any set in stone thresholds on that. The different calculation approaches make different assumptions there. So one approach that is sometimes used is a buffer approach, where you assume that the main contributors are those tanks within, let's say, 200 meters. On the other hand, something like Arc Inlet, I found that tanks up to a mile away, if you have a steep gradient and a sandy substrate, can have an effect. So it's site-specific.
It's very site-specific.
Yeah.
It is probably the most site-specific answer of anything you do in Bathtub. So that's definitely a look at your system, look at your geology, look at your soil, look at your tanks, make your best judgment.
Okay, I'm going to revisit a question from previously. Is there someone at the Army Corps of Engineers who currently maintains this model, someone you can call up at Army Corps? Do they have a website? If people have more additional questions about the specifics of the model or potential feature upgrades, things like that, how would people go about doing that? What's the answer to that?
I mean, at the Army Corps, Dr. Sobal is pointed out, is identified as the contact person.
He's retired.
But he's retired. And we've found that, like most folks who are retired, he has more important things to do than go and answer every question. So I think in unknown for the bathtub model, this is Ansel, the person speaking, not any agency. And unknown though is what is the future of it, right? Because the current formulation was come up with, were sort of coded in 1999, and will eventually it'll need to be modernized into another architecture. But I don't think anybody knows what the plan for that is, whether the Army Corps would like to play a role in that or not.
Got it.
So if there's someone out there that knows him, I think someone said they knew him personally, if he's willing to contract or work with someone, I know Florida is definitely interested in, updating and or, working with other agencies to keep this as a viable option.
Sure, yeah, and for people who are potentially venturing in for the first time to the bathtub model, it may make things a little more difficult to get started. I would assume that there's no active trainings or anything like that going on as well, right?
Not that I'm aware of. I think this is one of the first.
Okay, sorry, that was a Jason question. So back to the presenter, the audience questions. How are the point sources, when you're considering point sources in your model, similar to the septic systems, how do you handle point sources that are located? The question is 5 miles or more away, but it could be, I guess, any number of miles. How do you include those into your bathtub model?
So there's two questions, I guess, in terms of it. The first component might be how do you input it, and you can input it, the point source as a tributary. The second part is implied with the distances, do you put attenuation on it? And that depends on how you're setting it up. If you want to assume a worst case, you can apply no attenuation, or you can, if you want to apply an attenuation rate, either a watershed, using a more sophisticated watershed model would allow you to evaluate that, or you could collect data simply a downstream transect and measure attenuation. Either approach would make sense.
Okay, we're getting towards the end of the question, so I might advance a slide here to just do a little advertising before we get to the last few questions. Erin, I'm not sure if that's you or our meeting presenters who are going to do that.
I am not online. It's just Ansel.
There we go. There we go. Okay. So yeah, just a little more information for folks. Again, the contact info for Erin and Ansel and myself, Jason Gilday, our surface modeling workgroup website, where you can find links to all of the webinars that we've done to date. In addition, we are trying to update that website to include various trainings and things, and look for some updates in hopefully the near future to be a little more robust about various modeling training opportunities throughout the U.S. And I believe the next slide has an advertisement for our next webinar, which we're working on scheduling for later in August, and that's the Illinois River Modeling, which will be presented by Dr. Taimur Sheikh of EPA Region 6. And I think we have time for a few more questions, Ansel and Erin, if you're up to it. Could Bathtub generate year-specific model results? In other words, the question is, I thought Bathtub is a steady-state model.
It depends on, right, so it's a steady state model, so that steady state could either be a number of years, or you could assume each year is its own steady state.
Yeah, and some of the examples, we've done both in Florida.
Yeah. Okay. And have the load predictions made by your ARC program, I think, which was called ARCnet?
Inlet.
Inlet, thank you. Have the load predictions made by ARC Inlet been compared to in-lake data, say collected from seepage meters or very, site-specific information?
Not in lake, but there were some calibration studies done in the Jacksonville and St. Lucie, and they compared the ARC Inlet predicted groundwater concentrations to well data. So the rates there are sort of compared that way. And like any model, if you want to make really accurate predictions of that model, so it's sort of a luck thing, right? Because your wells aren't everywhere. But if you happen to have a well that's in the line of some of those plumes, you can actually look at your nutrient concentrations in your well and compare it to the ARC Inlet results and ground truth that. So.
Yeah, and that's part of, as I mentioned, there's a link on the slide to Ming's website as well as some YouTube videos, and he's talking about that because we have realized as well, based on soil and some of the different areas throughout Florida, that we're getting somewhat different results, and the model needs to be calibrated slightly different, and that's why local municipalities as well as DEP ourselves contracted with him to do those studies, put in monitoring wells, and actually help us refine that calibration and kind of the do's and don'ts of that model.
Okay, great. Another question. I think we're about wrapping up here. I think maybe I will summarize a few questions. With chlorophyll A is obviously, and algae is obviously variable throughout a year. So how do you account for that? The presence of absence or algae blooms, or varying algae blooms that happen throughout the year?
Florida is very data rich, and sorry, that's one reason we love Florida and work here. A lot of the lakes we work on, we have at least at minimum quarterly data, if not more than that. So we use real data to help us determine that. Obviously, the time scale is not super fine to catch every bloom, but we are able to capture that on the annual basis. I don't know, Ansel, if you want to elaborate on the Cadillac model of having extensive weekly data, weekly, monthly.
I mean, that allowed us to get a really accurate average, and Bathtub is giving you an annual average, so we were sure. And if you were to look at, this is more of a data thing, if you look at any lake that has blooms, if you compare annual average chlorophyll with the maximum observed chlorophyll, generally there's a relationship such that if you get that average chlorophyll down, assuming we're talking about a nutrient reduction scenario, you'll reduce the maximum peak height of the blooms, or you might find a nonlinear dynamic where you just don't get blooms below a certain point. So that's you'd probably want to do data, but that could be an important analysis if you're trying to prevent a particularly acute situation.
Well, I think with that, why don't we wrap up the webinar a little early? I have just a few more slides to cover, but I just want to say a huge thank you to Ansel and Erin for your presentation today. I encourage people to reach out to both of them if you have questions about anything they presented today. Also on the screen, you'll see that we've posted how to subscribe to future water modeling workgroup webinars and general updates. You can go to the link here at the EPA Office of Water. There's an email listserv that you can sign up on. That is the primary way that we are distributing information about these webinars now, in addition to updating our website, which was, you had the link earlier, whenever a new webinar is advertised. So with that, thank you everyone for joining today. Please don't forget that an evaluation will pop up here at the end of the webinar, and I encourage you to fill that out and let us know what you thought of the webinar and potential future webinars. And Ansel and Erin, thanks again. We really appreciate this.
Thank you for inviting us. And like I said, reach out to either one of us if you all have any questions, and we'll get back to you as soon as we can.
Okay, with that, we're going to end the webinar. Thank you, everyone.